Okay, so welcome everyone to our Section 83 ENSA class. I appreciate everyone being here. I'm going to share my screen. If you have any questions, I thank you also for being understanding about last week. My back was just in terrible knots. So anytime the weather makes big changes, I usually suffer unmercifully, but thankfully it's not quite as bad today. I want to ask if there are any questions about access control list or questions about anything we've gone over previously before we get started. You're going to notice today as we talk about NAT, the integral role that ACLs even have in NAT, because you have to create a NAT ACL to say what gets NATed. And there's so many places inside of the Cisco iOS where access control lists are used for different functions other than just a permit or deny statement for security. So we're going to see that today as we talk a little bit about NAT. And then we're going to be talking about NAT for IPv4, not really about IPv6, although there is technically NAT 6 to 4, which is a way to NAT from 6 to 4. But the whole entire design ideas behind IPv6 is there would be no NAT, that everyone would get a public IP address. Let's talk first about this IP private address space. We all know RFC 1918. We know these 10 groups, these three groups of addresses here, the 10.0.0/8, the 172.16 to 172.31, and then the 192.168.00 to 192.168.255.255. 3 blocks of addresses that are considered to be private addresses or addresses that cannot be routed on the internet. In fact, all of your internet service providers have, unless they're actually extending these private addresses as part of their internal network, most of them have on their routers connected to their customers an access control list that will send any of these IP addresses into the bit bucket. That way, if it accidentally leaks outside somehow through a configuration error, these private addresses will be sent to null 0, which is basically the bit bucket. So if you ever see that on an ISP's router, that's what they're doing. They do not want your RFC 1918 addresses making it onto their network. But the reason that's important to understand is we use these internal private addresses inside because they're the easiest for us to do our subnetting and numbering with. So we've got to have a way in order to get actual public IP addresses, and that is NAT, or Network Address Translation. So you do this at home. You do this on your little home router sitting on your network, and we do this in small businesses, large businesses. We all use NAT. In fact, if it wasn't for NAT around 1999 or year 2000, we would have all had to have switched over to IPv6 because we've been out of IPv4 addresses that long. But NAT has allowed us to continue to use IPv4 private addresses inside and then have the outside addresses NATed to 1, 2, or just a couple external public IP addresses. The rough estimate that Cisco says is about 4 million different connections can be handled by a single public IP address. Now, that's not 4 million hosts, because remember, just like my machine right now is connected to the network, it probably has between 50 and 100 connections open easily out to the internet somewhere, because I'm connected to, my this Zoom call, I'm connected to Netacad, I'm connected to all different things. So it's not 4 million devices, it's 4 million connections per NAT IP address. But that still means you can support a fairly large network with a very small number of public addresses. The only negative to that is, depending on the type of NAT you're using, our typical NAT does not have the ability to actually track back all the way internally to what the host was that originated the connection for a forensic purpose. It's difficult to do that. Not impossible, but it's difficult to do that because of the fact that my machine right now could be going out with one IP address. Tomorrow I could go out with a different IP address, depending on how NAT has been set up on Stanley's network. But here it is, stub network, private address space inside of the 10s and 192s. We have a NAT-enabled border router, which will then basically translate between the public and private IP addresses. So here's an example, real simple. You got your internal address. Now, I will tell you that for reasons that are just some of it's for confusion, some of it is because there are cases to where you NAT between two networks, both running the same internal internal private address space. That is why Cisco has this inside local, inside global, outside global. What it comes down to is the inside local is the private IP address inside. The inside global is the address that you're going to be NATed to, the actual public address. Outside local is the device you're going to, and outside global again is the same. So outside local, outside global, these are the same because those are a public outside address you're going to. But the inside global is what you are NATed to by the NAT device. I really personally just like saying inside outside because it's just somewhat simpler for our students, but they will see this in the tables when they run the labs, and they will see this when they're reading about Cisco's devices. So it's important that they at least understand what's going on here. So again, inside local address, inside global, this is the private address as shown here. Inside global is the address that private address is going to be NATed to. So it's a public address that will stand in for that inside local. Outside local address is the actual public address you're going to, and outside global is the same in most cases. It's not always. If you had a situation where you were NATing both ways, they could actually be different. The outside local and outside global could be different. But it's very, very unusual that that happens. So just be aware that's why that exists, is in case you ever had to NAT between two spaces, both using the same private addressing space. So source address, destination address, that'll show you those, and then we can see how they're being NATed. You will notice in this particular chart, it's an IP address. There are no port numbers. So if I see this chart and I'm asked, what does this chart show? This tells me they're not using port address translation. This is some type of one-to-one mapping of an inside to an outside IP address because there's no ports. If the ports would have been showing, or if there's different ports, then that's what's called port address translation. But this is just typical NAT. Now, I have some disagreement with the curriculum on how they talk about NAT, and I'll tell you where that I veer from them in just a minute. But I don't disagree with static NAT. Static NAT is one-to-one. In other words, if you've got a device on your internal network or your DMZ, more than likely your DMZ, not your internal network, because you don't want to punch holes into your internal network. But you may have a web server on your DMZ or an email head-end server or something of that nature that needs a public IP address, and it needs to be the same address all the time. Well, for that, we use static NAT. We take a one-to-one translation to say this server, 192.168.10.10, and it should be 10. Notice that they're missing a dot here on all of these, okay? So that should be 192.168.10.10, not 192.168.10.10. All right. But this machine here, this server is being NATed one-to-one to this 209.165.200.226 address. So just be aware that is what is called static NAT, one-to-one, used mainly for those devices that need to be accessible from the outside on a public IP address. Now, dynamic NAT is one to a pool of addresses. So I call it, let me get my notepad out. My wonderful notepad. So we've got static NAT, for some reason static NAT. So this is one-to-one. I call dynamic NAT is one to a pool of public addresses, or actually many. Well, actually it's one to a pool. I cannot type of public addresses. But what most people don't know or don't realize is that with dynamic NAT, even if you're using a pool, once you do all your one-to-one mappings, let's say you put 4 addresses in the pool and you've got 5 or 6 hosts on the inside network. By default, even if you don't put overload, what the Cisco IOS typically does nowadays is it will do one-to-one mappings until it gets to the final address in the pool. and then it will start automatically doing overload on that final address. Now, I want to explain to you where we've just run into a problem on that. In the very lab that we have here, in our lab for NAT for IPv4, we set up in our classroom. These PCs down here, there are only 2 PCs, but these PCs were running Windows machines, and they're typically on Stanley Community College's full actual network. So in this lab, when we got to the part to where we set up the NAT with a pool, okay, before we ever did the overload, so there was no overload. It was just, we created the pool. Let me find my pool here. We created a pool right here. All right. There's no overload on this pool, so we don't have dynamic NAT with overload yet. But my instructor came to me and said, why am I seeing port addresses being used? Well, what was happening was this. These PCs, because they were Windows machines, even they were trying to go out on Windows services. So there were multiple attempts from Windows services going out. Well, this pool only has like 3 addresses in it, 3 or 4 addresses. Actually, it's got 3, 226, 227, 228. Well, what happened was the first 226 was used, then 227 was used, and then there were more requests. And because of that, this last address 228 started getting padded or NAT with overload. And that is what happens by default when you set up a pool. It will do a one-to-one mapping until you get to the final IP address in the pool, and then it will start doing NAT with overload automatically. Okay, so that's where I call, they say dynamic NAT, I call it also dynamic NAT with overload. And that is one to a pool of public until the last IP that is then overloaded. The curriculum just calls that PAT, port address translation. This I call mini internal private to a shared IP public on an interface. That's what I call PAT. So the curriculum and I disagree. It happens. Okay. Now for the test, here's what I always teach my students. There's a test world. All right. Do what the curriculum says. There's a certification world where you do what they want on the certification exam. And then there's a real world where we actually tell it the way it is. Okay. So in the certification world, we call it PAT for anything that is overload, whether it's done inside of a dynamic NAT with an overload to a pool, or if it's overloaded to the IP address that's actually assigned on the interface. Real world, I call PAT, it has to be an IP address assigned on the interface that's being also overloaded to. Does that make sense? Okay. So again, if we had this pool right here, and they don't really talk about it in the curriculum, so when it happens, people get confused, but there's a one-to-one mapping for all the addresses until the final one. And then when you get to the final one, it starts overloading on its own. It basically has figured out, ooh, I'm running out of addresses, so now I've got to do something to support more internal hosts. Used to be, it wouldn't do that. It would just stop anybody else from being able to do it. And they were like, well, that's a mistake, so we're going to go ahead and do that anyway. All right. So PAT, also known as NAT overload, again, don't agree with that. I think they're 2 different things. That's just me. PAT is many inside to one outside address. Typically, that outside address is already assigned to an interface on the outside. So you'll notice in this case, they're all being NATed to 226. You'll notice it's got the source and destination ports because it is dealing with port address translation. So here's another problem. If, think about it, whenever you do a connection between a host using TCP or UDP, it picks a random port number. Well, there is the off chance that two inside hosts could pick the same random port number. If that happens, all NAT does is it increments it by 1. So here we have an instance port 1444 is in use. Another host comes in with port 1444. It simply increments it on the outside, and as long as it's got that outside knows it's 1445, when it comes back in, it'll send it to 1444. So in other words, it can handle that. It just handles it in the NAT table. Not a big problem at all. So our comparison is NAT's one-to-one mapping between inside and local, uses only IPv4 address and translation process for NAT, and a unique global is required for each host on the inside. PAT uses one global address to be mapped to many inside locals, and then it also uses TCP and UDP port numbers. So, now what are some advantages of NAT? Well, obviously we have not run out of IP addresses yet. There's some debate on whether or not it gives us any security. I will say it does hide the internal structure of your network better than if we didn't have it. Is it more secure? Probably not. But it does give us more flexibility on the inside. It also makes life easier for us. Let's think if we change ISPs or something of that nature, because we don't have to renumber our entire internal network. We can literally just renumber the external portion of our network that connects to a new ISP. So there's some huge advantages there. Disadvantages is we do lose that end-to-end connectivity. It used to be a long time ago, not a big problem now, but it used to be certain applications would break due to NAT. Those days are long over. Even things like FTP would give us problems. Xbox was terrible with NAT. It didn't like it because it would lose things. Not an issue anymore. All that's pretty much been handled through NAT traversal and other issues. So we don't really have to worry about that so much. I will tell you where things are getting a little bit sketchy is in places like India, where there are certain areas of India where there's 7 to 9 layers of NAT before you get to a public IP address. So think about that. It's being NATed 7 different times through private RFC 1918 addresses before it ever gets to a public address. You are never going to trace back somebody hacking from one of those IP addresses. It's just not going to happen.
Yeah, I've seen small ISPs with the same thing. They do NAT. They only get a handful of IP addresses from their provider, and they're NATing through all the different neighborhoods.
Definitely. You've got an RFC 1918 address in the house, an RFC 1918 address going from the house to the ISP. The entire ISP central core is RFC 1918. And then it never gets NATed until it gets out and goes to another entire autonomous system, which is kind of crazy. But yeah, that does happen. So let's look at configuration. It's actually pretty simple. Here's an example of we're going to do a static translation between 10.254 and 201.5. So we're going to go in here and we're going to do IPNAT inside source static, inside outside. I'll make it into a little sing-song. IPNAT inside source static, inside outside. Because then you just remember you've got inside address and then whatever you're mapping it to outside. Then where people always mess up is they forget to set what's inside and what's outside. They create this, but they never say what interface is inside, what is outside. So you got to go and set your inside and outside IP address or your interfaces. The other thing people get in trouble with is if you have sub interfaces, you need to set inside on all the sub interfaces if they are to be NATed, because those are all inside. You want to see a static NAT? You just do show IPNAT trans, and it will show a single IP address being mapped to that host. So IPNAT trans, you see that the inside local is 254, the inside global is 201.5, and we have effectively created a one-to-one translation of NAT between a private and a public IP address. Now, the negative with this is most of us won't get very many true public addresses anymore. I'm doing a lot of study on AWS right now, and it's interesting how AWS, they actually will give you public addresses, but if you don't use them, they will charge you for them. But if you're using them, they actually don't charge you for using the elastic public IP address. The reason being, if you're using the address, guess what? They're getting your money some other way. They're getting it through compute or through storage or something else. But if you take a public IP address and you hold on to it and don't release it and don't use it, you actually get charged for it because it's been taken out of the pool. It's a weird setup how they've done that, but it makes sense because they figure if you're actually using it, you're moving data, they're charging you money. So it's a very, very interesting thing. Okay. So static NAT's easy. Dynamic NAT is a little bit different, but not much worse. First off, what we're going to do is create a pool of addresses. So we're going to define what can we NAT to. In this case, we've got a pool called NAT pool, and it contains the addresses from 226 to 240. And you'll notice this is very important because we're going to use this a little bit later to apply this NAT pool. Okay, and I'll show you apply it to an ACL. So we create our pool. We create a standard ACL that I call the NAT ACL, and that ACL is to determine what can be NATed. So this access list says anything that comes in from 192.168.0.0 can be NATed, or should be NATed, actually, should be NATed. But then we have to put them together. IP NAT inside source list 1, pool NAT pool. That's why it's so important that if you mistype, if you make this all caps and you made this all lowercase, it would not work because the all lowercase NAT pool 1 doesn't exist. Cisco routers are case sensitive. But this basically says anything that matches access list 1, NAT it using this pool. But guess what? You still have to do your inside and your outside interfaces so that it knows which side's inside, which side's outside. So this setup would have created a pool that anything that matches this coming in S010 would get NATed going out S010 or S011. A one-to-one translation. Now again, what they don't teach you in this is typically it will do a one-to-one translation until it reaches that final IP address, and even without the overload command, most versions of the iOS now will overload on that final one. So if you see that in your lab, don't freak out. That's why it's happening. All right, it's just doing it automatically. So we look at a show IP NAT trans, we'll see this. You'll notice that each address is being mapped to a different IP address from the pool. Just be aware once the pool runs out, that final one is typically overloaded again. If you ever need to clear translations, you can always do a clear IP NAT trans star, and that will clear out all the translations in the translation table. We use that all the time, especially when we're making changes. We made a mistake. Some things have been NATed. We want to get rid of it. Clear IP NAT trans star. Right? Now, PAT, a little bit different. We can PAT to a single IP address by doing this. IP NAT inside source list 1. And this, we still have to create a NAT ACL that says what should be NATed. But then we just say interface list 1, interface S011 overload. So what this would do now is it would take whatever IP address is on serial 011 and it would NAT with overload or PAT everything that comes through that particular interface if you set the inside and outside correctly. You still have to set inside outside, always. And that has to know what is in and out. Now you can do it with a pool, so you can actually do it like this. Create a pool. Your access list still there, and then when you put them together, IP NAT inside source list 1 pool, NAT pool 2 overload. This will, by the way, still do exactly what I was talking about before. It'll map 1-to-1 till it gets to the final one, then it overloads on the final one. Okay. So it'll do 1-to-1 until it gets to the final one in the pool, then it overloads. But you still have to set inside outside. If you don't, it won't work. Will not NAT. Okay. So let's jump over here real quickly. I want to show you, here's our lab. We've got this right here. I've already set up R1 and put these IP addresses on it. I'm actually going to pull this content out so I can put it in a different window over here. So I'm going to put it right there. And then I'm actually going to go into R1 and I'm going to dock R1 back in here and I'm going to dock R2 back in here. So, but I'm going to pull this right there. Okay. I'm going to try, give me a second so I can get the stick. All right. Wrong one. I want this to stick there. There. All right. So R1. So I'm going to set up NAT on R1. Not R2, R1. So I've got inside, you'll notice all my addresses are a 192.168.1.0. So the first thing I'm going to do on R1 is I'm going to create my crypto ACL. Config T. So I'm doing access list 1 permit, and I'll just do 192.168.1.0. I'm going to be as specific as I can. I could have done 192.168.0.0 and a /16, but I'm going to be specific. Okay. So I'm permitting. That's what I want to be natted. Okay. Then I'm going to go ahead and I'm just going to do a pat. I'm going to cheat. I'm not going to do a pull. I'm just going to overload to the outside interface on R1. So I'm going to do IP NAT inside source 1. Okay. And you'll notice that list 1. And then I can do an interface G000, and I'm going to type overload. Okay. Boom. Now, I need to go and do my inside and outside statements because I haven't done that yet. So looking at this, what should be my inside interface on R1? What should be my inside on R1?
G001, right?
G001. Yep. So that's my inside. So I'm going to go to interface G001 and do IP NAT inside. Then I'm going to hit the up arrow because I'm lazy. I mean efficient. And I'm going to do IP NAT outside and boom. So now at this point, NAT should work. Now let me show you something that confuses people all the time. I'm going to exit out of here real quick. I'm going to exit again. I'm going to try to exit. Okay. Now I'm going to do a show IP NAT trans. You'll see there are no translations. Right. I'm going to ping R2. So ping 209.165.200.225. All right. I still have no NAT translations. Why? I just pinged between these two.
Yeah.
Why did I not get a NAT trans?
Well, we don't need it yet, right? Because the PCs haven't done anything.
Key point. When I just did this ping, by default, when you do a ping, the closest IP address to where you're pinging is used. So I pinged from a 209 address, so nothing has gone through to be natted. Nothing is needed to be. So what I can do is this. Let's use an extended ping. Okay. So let's do ping. Protocols IP. Target IP address is still 209.165.200.225, which is R2. Repeat count, I'm going to actually say 10. Datagram size, timeout 2, that's fine. Extended commands, yes. Ingress ping, no. Source IP address. Now I'm going to source it from 192.168.1.1, which is the IP address of G001. Now, I just hit enter a couple times, and I should have a translation here. Yep. Notice how I've got a translation. Because I pinged from an IP address that matched my NAT ACL. Previously, it didn't match the NAT ACL, so it would not have pinged. And it never crossed the router either. So now you can see from what we've got here, we've actually got an actual inside local, the 1.1, which was the IP address we pinged from, and it is being natted or padded. It's actually been port address translated to 230 using a port number 1. Now, if we put our IP addresses on our PCs, so we go in here now and we find get our IP addresses on our PCs. So if I go in here and get my Ethernet, change adapter settings. And let's go under here and go to properties. Change it to 192.168.1.10 and then 192.168.1.1. Click OK. Close that. Let's get our CMD up. CMD. Let's do IP config. We got that ping 192.168.1.1. Yep, we have pingage to our default gateway. Now let's ping 209.165.200.225. We got pingage there. So we go back over here and do a show IP NAT trans. We should now see, we should have seen another translation. And I am not seeing one. Why am I not seeing another translation? 201. Hold on. Maybe
Well, yeah, you see it. We see the translation for the PC, but now the translation for the router port's gone.
Correct. Yep. So let's go back over here. No, it's yeah, you're right. 1.10. Yeah. So we lost the other one. Exactly. So let's do this. Let's get PCB up and we'll start continuous pings and we should be able to see both at that point. Wow, my mouse is doing weird stuff. There we go. Yep, so we picked up 1.10 instead of 1.1. Now we can go here, adapter settings. We will go to 192.168.1.11. 192.168.1. Here, here. Go here, and we'll ping 209.200. 165. 165.200.225. Now we should now see two translations. Nope, still seeing one because the other one's not pinging two. So let's do this. Let's do a ping dash T. B. Now we should see. There we go. Now we got two translations. Yep. We just had to play with it till it would do it. So
Okay, so whenever you do this command, it just shows whoever's currently active or the last translation that was made.
right, and it will also there is a timeout period. So ICMP has a really short timeout period. That's why it was dropping so quickly. You would have seen typically in a real environment, these things stay up longer than that because it's not ICMP, it's actually TCP or UDP or something going out. Yeah, so they typically stay longer. Like I said, the big problem we've seen is don't get confused if you start seeing a large number of translations in there, even though you're not doing anything, especially if you're in your lab and these machines are Windows machines, because they will be trying. And in fact, what we were seeing is the services inside were attempting to do NAT using the IP addresses and was going to weird ports, but it was all the Windows services on the boxes going out. So just realize if your students see that, that's what's going on. You'll see here how that's already timed out on PCB because that's ended. So it's already dropped it out of R1's NAT table. But now if I wanted to clear it, I could do a clear IP NAT trans star and it will clear the table completely. Well, other than the fact that other one's pinging constantly. So I got PCA over here doing a continuous ping. But if I do a clear IP NAT trans now, all the trends will eventually be gone. Huh, that thing's still doing it. Must not have stopped it. I didn't. It didn't take my control C. Stop. There we go. Now to do it. There. So clear IP NAT trans star, that gets rid of it. But you'll see it's not hard to do, Pat. It's really not hard to do any of these. But the big thing is you need to make sure that you're using the correct version for what you need to do for your particular network. Don't forget too, you could do a static NAT, and then that way you could get connectivity inside. But that's something that we don't normally punch a hole all the way in. We punch a hole into the DMZ. And more today, our services reside out on the cloud, and we don't even punch any holes in our networks. We stick them out in the cloud and make everything stay out there so it's away from us. Questions on NAT or PAT? This will show up on the hands-on final for this exam. And I can go ahead and tell you, this is a major topic that you almost always see on the CCNA exam, because it is such an important concept. This is something, to me, this is one of the vital important things in ENSA that your students need to know how to do and need to understand, because everything from our home networks to ships at port running in and hitting a head in and getting that, this is used everywhere. This is absolutely everywhere. Okay. Now, this not so much. This is what's called NAT 6-4, and this is it's funny, they teach you this and they say we actually recommend you run a dual stack network instead of NAT 6-4. So it's recommended that you have everything running both. But in an example where you've got only one, so only IPv6 or only IPv4, you can actually run a 6-4 to allow IP addresses that are IPv6 NATed into an IPv4. They've even got another thing that's in there called NAT-PT that's been depreciated, but this just gives you a basic understanding of what it is. IPv6 does have its own private address space, but it was created to be like 1918, and then suddenly they were like, well, we really don't. The reason we want to go to IPv6 is to stop these end-to-end connectivity issues, not being able to see end-to-end. And so they've kind of depreciated all of those, the NAT capabilities of IPv6. We used to have to learn even how to do NAT 6-4 and how to do NAT-PT, but we don't do that anymore. So just be aware it's out there in case you would have to use it, NAT 6-4 or NAT 6-4. All right. Any other questions? Any questions at all on PAT? NAT, PAT, any of those? Okay, I'm going to blow through Module 7 real quick because this is a real easy module. I always get tickled about WANs because we always talk about high-speed internet. How fast is your internet? Mine at home now, I will say, since I've got Starlink, it's much faster than it used to be. So I'm getting between 80 and 140 to 150 megabits per second down and about 10 to 15 megabits up, depending on what time of day it is, what the weather is. But we always talk about high-speed internet. What is the slowest NIC you can buy on a PC today that go in your lab? Probably a gigabit, right?
Yeah, I haven't been shopping for slow cards lately.
Yeah, but yeah,
sure
that's what I'm saying.
out.
Just to buy basic NIC, it's going to be a gigabit NIC. Well, how many of you have gigabit internet at home?
Mine's like 367.
Yeah, not many people have gigabit at home. Now, there are more people today that have it than used to have it. But it's so funny we talk about high-speed internet and high-speed WAN connections when most of our WAN connections are not really that high speed. They're high speed what they used to be. But we talk about WAN connectivity. WANs provide large geographical areas, large connectivity. We have public-private WANs where we've actually, and I'm reading more and more again, looking at AWS, how you can do connectors into your data center so that your data center can directly connect AWS services and appear to use the services that are on AWS. But, we don't have as much of that as most people want because it's so expensive. Here's a point-to-point link. We've all seen those. Here's a hub and spoke. Dual homed, which is where you're connected to multiple ISPs. Now, this is a best practice that you actually connect your network to multiple ISPs. Fully meshed, okay, and then of course our partial meshes. Our greatest example would be dual home with full meshes, but as soon as you do that, money costs go sky high. So you have to be, there's a lot of times we end up with a partial mesh topology or something of that nature because we can't afford the cost. So here's a single carrier, and then this is what is called dual homed or dual carrier. It's actually even better if instead of doing it like this, is if you can have 2 routers on your external edge of your corporation and have one of those going to one ISP, one going to the other. One thing that does happen as soon as you become a dual homed entity, you typically have to run BGP because it's the only way to ensure traffic can be routed out and get back correctly for in most cases. So that I will say, when you become a dual homed or a dual carrier WAN, you're going to have to deal with the headache that is BGP. So evolving networks, small home networks, our campus networks like this. By the way, I will say our campus networks have changed even just since I've been working. It used to be we were layer 2 out to every building. Now we don't do layer 2 to every building. We do layer 3 to each building. So we don't have VLANs that exist across the entire campus. The VLANs are inside the buildings. Then the buildings are actually layer 3 entities that get summarized down to the core. That's something that's taken place during my time in networking. We used to have layer 2 that went across the entire enterprise, but no more. We've done away with that. Branch networks, more and more, especially as we're working from home and away and remotely. The great thing about technology is we're always connected. The bad thing is we're always connected. I'm going again to Adepticon tomorrow to go and play some games this week. But I guarantee you, someone will be emailing or calling or texting me because they're going to need something. But we've got to build our network so that we have the ability that if I am in, up here in Canada, I'm able to respond to emails. I did find an interesting thing out while I was in Canada. My Office 365 applications would not work on my laptop when I was in Canada, unless I VPN'd into the United States. So they've set up a policy through Office 365 that our apps won't work if you're outside of the US. So I'm glad I had easy VPN, Express VPN installed on my devices. So some WAN ops, looking at some of the standards. Most of these standards are layer 2 standards. So it's EIA, TIA, and IEEE standards, ISO standards. A lot of layer 1 protocols are things like SDH, SONET, dense wave division multiplexing. Then layer 2 protocols, you're getting into Metro Ethernet, wireless, broadband. One of the things they don't mention here about in this is that we have moved now into the era of low Earth orbit satellites, LEO. Starlink has made major changes to the industry, especially, they're getting ready to start rolling out the test to where cell phones on the T-Mobile network will be able to use satellites as their carrier service. So if you're somewhere you're up in the Canadian Rockies and there's no cell tower around, your phone can connect to a low Earth orbit satellite and use that for its voice calls and data connection. And that's coming. That's actually part of the version 2 satellites that are being launched now. I just found there was an interesting thing that just happened when I was at Cisco Live last year. A lot of discussion about companies that were mining companies and construction companies, because their actual employees were going out and buying Starlink to place on site so they would have high-speed internet on site. And there was a lot of complaints about how Starlink doesn't have a good, by the way, it has a terrible support set up for enterprise networks. Basically, there's no support for enterprise networks. So there's a huge service out there for somebody that would buy and resell Starlink if that's something Starlink will allow. But you think about it, I never thought about that. Mining takes place in areas that's out in the middle of nowhere. There's not going to be cell towers out there. There's no way to get internet service to those sites. Not so funny, just recently, an illegal mining operation in a place in Africa was found to be operating via the use of Starlink. So they had created an illegal mining operation and were using Starlink for their information, to be able to do their data transfer and information. So a lot of interesting things going on. These are some of the old terms: DCE, DTE. Just remember, with DCE, it provides the clock rate. So data communications equipment, DCE. We used to have serial links in our in the CCNA, and we had to set clock rates on our serial interfaces and all those things. We don't do that anymore because we don't have serial links on any of our gear. WAN devices, DSL modems, cable modems, CSU, DSU, carrier sense unit, data service unit, optical converters. All of those are things we've used in the past. Here's an example. You do need to know the difference between serial and parallel communication. In serial, it's 1 bit at a time. In parallel, you can put a large number of bits, typically 8 bits at a time together, and get bytes being sent. So serial is 1 at a time. Parallel is putting multiple bits on the line at the same time and being able to transmit it. Okay. Circuit switch, this is the old way it used to be. If you ever seen the old TV shows where the lady, or it was a lady, I'm not being sexist, just true, who were the operators back in the day, and they would get a call and say, I need to talk to Bob. And they'd literally take and put a cable between the 2 telephone lines in the office there. That's circuit switched. It builds a circuit, the circuit is in use, and then the circuit can be torn down at the end. That is kind of the old way things were done. Today we use packet switched. In other words, we break everything into packets. We throw it out on the network and say, we hope you get there. Of course, we have at layer 4 with TCP and at other layers, mechanisms to deal with lost packets and mechanisms to deal with the ability to put packets back together when they're received on the receiving end. So the good news about packet switched versus circuit switched is it can easily get around errors and problems with the network itself. Okay, good, I went down. All right. Here's some of the standards you probably haven't heard much on, but synchronous digital hierarchy for its global standard for data over fiber optic, and SONET North American standard for the same service as SDH. One of the cool things about fiber is, one, there's no loss on fiber. Technically, there is a little bit though, because of the fact that you still are going through a media or medium. We don't know how much data can be transferred through fiber. I mean, there's really theoretically no limit. So we're dealing with whatever we can put on it, the lasers we can create and the technologies we can create to read those laser pulses are that's what's slowing us down, because data can be sent at the speed of light, but it can't be read that fast. But as we continue on, obviously the use of fiber optic cable will allow us to really greatly expand what we can send. Here's some traditional WAN connectivity options, dedicated leased lines. Almost nobody does this anymore unless it's for security reasons. Most of it today is packet switched. We really don't even use, I mean, have any of you even heard of a frame relay circuit in the last 5 to 10 years? I hadn't, not in the US. Now, maybe I did have some folks who were working business in Mexico, and they were dealing with frame relay as close as 8 years ago, but that was still 8 years ago. PSTN, almost nobody uses public switch telephone network anymore. ISDN is definitely legacy. That's way gone. We just don't use it. By the way, there was a day in the CCNA when we had to actually learn to configure ISDN. That was a lab that we worked on in the CCNA. Back in my day, God, I'm getting old. Okay. And folks, I'm gonna stop there and just let y'all look through the rest of this. Most of this you all know. The only thing I will check on here is MPLS. Most people don't know about MPLS, but I want to mention it's honestly what MPLS is. It's the concept of VLANs in a service provider's network. So you put what are called labels or flow labels or switching labels or tags in the service provider's Metro Ethernet network. You put MPLS tags on it, and then that traffic can travel across the same infrastructure as other businesses, but they won't interfere with each other because they don't even see each other because they have different labels. It's just like VLAN tags. If you're not on the correct MPLS tag, you're not visible. So have any of you worked with MPLS? Any of you done any actual MPLS implementation? I hadn't either. I hadn't actually rolled it out. So you've got a cloud here, and basically you connect to the MPLS cloud, and as traffic comes in, it is tagged, and it stays tagged inside the MPLS cloud. When it gets to the receiving end, it's untagged. So it is almost exactly like the concept of VLAN tagging with .1Q. All right. All right. So again, a couple things here: broadband versus internet-based VPN. WiMAX, satellite internet, all of those. They got a little bit in here about the newer stuff. I would, obviously go over all these, looking at cable technologies, looking at optical fiber, fiber to the home. This was really big there for a while. Google was. Ezra, you got a question? You got your hand up.
Yes, for
Right.
the MPLS, are these mainly for video transmission?
No,
MPLS
MPLS can be used for any traffic. It is not just for video, no.
Okay,
No, it can be used for any traffic whatsoever.
okay, thank you.
Yep. Optical fiber, there was that big Google fiber push there for a while. And it seems like Google's even kind of backed away from that. So I don't know. I don't know where we're going. I actually do think that, I hate to gush about Starlink. It may break tonight. Now my wife would gripe at me the whole time I'm gone, but it was stupid simple to set up. My satellite literally is sitting in my front yard right now. And it runs into the house through a window at the moment. I need to get it mounted on the house, and I haven't been able to do that yet because I can't climb a 30-foot ladder. But it works. And the funniest thing ever is, as soon as I think I've told you all this, as soon as I put that satellite in my front yard, I had DSL at the same also at the same time. My DSL provider increased my speed by 10 megabits per second and lowered my price on it. Of course, I canceled my DSL like 3 weeks later because my Starlink was working. But I think that's going to make a big difference in how internet gets to places. If these local entities can't find a way to catch up, they're going to be in trouble. The only negative about Starlink is it's a $500 buy-in and it's expensive. I mean, it's $120 per month, or $110 per month. But for the speed, I'll pay it. And in some places, a lot of the places I've been hearing about, like on Native American reservations, Indian reservations, they have no other internet. There's no way. I mean, there's one place in Canada that is so far remote in the Northwest Territory that without this, their school systems would not, the indigenous people would not have internet for their school system, and it works perfect up there. So it's kind of changing the way the internet's going to be deployed around the world, I think. I think we also saw that in the Ukraine, the fact that they deployed it for a command and control infrastructure. The only problem with that is now everyone is thinking of ways to destroy these low Earth orbit satellite systems. Which is super scary because they could cause a catastrophic cascade that would literally destroy all satellites in orbit. Which we're close to that anyway. If you've never read about the concept of a cascading storm of space debris, read about it because it's pretty darn scary. But okay, we'll get back together next week and talk about VPNs and IPsec and types of VPNs. But otherwise, folks, if you have any questions, I am going to be available via email. Like I said, I'm away, but I will be available via email. You can easily email me, and I'll try my best to get back with you as fast as I can. I am technically on actual paid time off, but I'm still going to try to answer the emails as much as I can. So if you have any questions, please feel free to send them to me. All right, I'm going to stop the recording.